I gave you the intuitive part, and then you have in the book, as I say, you have in the book that you have available, which are described, you have here, and they took it from the official book, which is the one they should give it to. But these are the formal definition. How is it defined in new space? How is it defined in the span space, and so on. Let's move forward. Now, as I said, we already discussed it. As I said, in engineering problems, the matrix A accounts for the model. So what is the model specifically? The linearly combines the minimal model parameter, so the columns, okay, with the scaling factor. If I need to cope with noise in measurement, okay, which means that I need to make the number of measurements larger than the unknown, this is what I usually do. I try to make it, very much with that. So it means that I try to make a matrix that is very tall. So we will handle 99% of the time tall matrices. Because if I have tall matrices, I create a redundancy, which means if I need to get the set of numbers, which are the parameters I need to estimate, and I have the data, so the data is redundant with respect to the number of parameters. We will see that this property is theoretically true. We will see that it is always theoretically convenient to have a tall matrices, because the accuracy of my estimator will depend on this ratio between how many unknown and how many measurements. Another operation that perhaps it will be common is if I have a vector, I want to rotate the vector. Okay? Now, if I have a vector and want to rotate the vector, so imagine that I have a set of my vector u1, u2, which are orthonormal one another, and I want to rotate into v1 and v2, then my rotation method is composed by trigonometric function, cosine and sine. Okay? Now, this is the rotation matrix. So the rotation matrix has a general property to be skew symmetric. What is a skew symmetric? It is, you have along the diagonal, you have cosine. And then it's sine and minus sine, which means it's the opposite side. It's the opposite, it's minus on the other side. So it's skew symmetric. Now, this is, the formula to rotate. Now, the rotation matrix, which is this one, has some nice properties, such that, for instance, if I apply a rotation and then a counter rotation, so I rotate it, then rotate in the opposite angle, I get the identity matrix, right? So that means that the inverse of the matrix is the counter rotation, because I rotate in the other side, because I have q theta, and then this one is the inverse of q theta. Because what is the inverse? The inverse of the matrix is, if I have a matrix multiplied by something else, I get the identity. And this is something else, is the counter rotation, so rotating on the other side. But this counter rotation is also the transpose, because it's skew symmetric. So this property that I'm now describing in two dimensions, this is general. So in general, if I have a matrix Q, and this matrix Q is a rotation matrix, then and then I compute the Q transpose. This one is equal to the identity, which means the transpose is equal to the identity. Okay, so in this case, if two matrices are composed this way, is a rotation. So rotation matrix is rotating the axis. What did we see with the quadratic form? You remember with the quadratic form, we had the eigenvector, and the eigenvectors were rotating. And then I said, those eigenvectors are rotating with respect to the principal axis. We are here. Here. Okay? This is what we discussed. And so we said, the eigenvectors u are rotating the axis. Okay, the property that I gave you in the quadratic form is general. Any rotation matrix has this property. Any. Now, so this is, you know, the rotation matrix for any size. So in case, you know, I have, set up one vector here, which is u1, u2, blah, blah, blah. And then what I need, I want to rotate the two with respect to two directions. So any rotation is carried out with respect to two axes at a time. So I rotate the two axes at a time. I know I have one axis 1, axis 2, axis 3. So what I can do, I can rotate one with respect to 2. Then I can rotate two with respect to 3. Okay? And this way I can make a composite rotation so that I can generate any rotation. Now, if I need to rotate the two dimensions at a time, the structure of the matrix is the same, which is skew symmetric, cosine, cosine, and then sine and minus sine. Now, you know, but this rotation matrix qij. Now, this is what's happening. So what I can do is, for instance, I can find my rotation angle such that this one is equal to 0. So I can rotate my axis such that one of the two dimensions is 0. Okay? Now, how can I make it? You know, suppose that I want Vj equals 0. So I make Vi is equal cos. Let me write cos and sine as a C and S. Okay? So this I write as C and this I write as S. Okay? So this is C Ui plus S Uj. Then I have Vj. Vj is equal to minus S Ui plus C Uj. Okay? Let's suppose that I want to make it equal 0. So my set of equations has to be written to calculate how is C and S. But remember, these are angles. So since they are angles, what I have the additional equation, which is cosine theta ij square plus sine theta ij square is equal to 1. So I put these equations and that one. And then I derive the theta ij, which is the specific rotation, which enables me to nullify one entry. Right? So why? Well, okay, these are, okay. Well, you know, I do this way because, I can apply this rotation not just to one entry, but to a matrix. So I can apply this rotation, for instance. Now, this is the sketch, okay? I can apply this rotation this way. Remember, it is a C, S, C, C, S, S, and minus S, okay? So these are the rotation. Let me write it. And minus S. Suppose that I apply that one, and what I do, I want to calculate the value such that the vector output has a 0. Okay, then I calculate my rotation such that the input matrices is 0. Okay, I apply one rotation. My output is that this one is 0. So I repeat. So I repeat again. And then if this one is 0, then I apply cosine, sine, then I make a rotation with respect to another pair of angles. And then I impose that this one is 0. So that is 0. And I repeat many times until my matrix becomes upper triangle. Okay? So these rotations are called Gibbs rotation. Here are applied, for instance, to reduce a complicated matrix to be upper triangular, and so on. Okay? So I can make any arbitrary rotation and blah, blah, blah. to clear the story. If I apply rotation on both sides, I am able to reduce, the matrix to be diagonal only. So I have a set of rotation on one side, a set of counter rotation on the other side. What am I computing? The eigenvectors. So eigenvectors are computed by rotations. Okay? And since rotations, is it clear? So since rotations are based on trigonometric functions, and since the trigonometric functions are, cosine can be derived by sine, by calculating the formula. This is the reason why in the computers there is the so-called sine table. This is a table of sine function. Because by the table of sine function, I can apply, rotation such that in case I have a complicated matrix, which is a complicated data structure, I can reduce this data structure to be, for instance, diagonal. Okay, I computed the eigenvectors. Now, okay, these are other. Okay, so again, just to summarize, we were talking about the projection. So the projection matrix, is just taking a vector and projecting on a certain subspace. So if I take that, whatever is the variable, x, we were calling b before. Right, this is b projected, this is b projected. So if I project, I'm projecting onto the space. This is p. If I project 2 times, so this is the point. I project, and then I project again. Okay, the second time, I don't change it. Because if I project it twice, it's like if I take my signal, I filter, then pass, then I filter a second time, then pass. It's the same. The second filtering doesn't change. Okay, so you can similarly say that if I project something that I projected already is the same, as the first one. So it's similar to make one projector only. So this means that the projection matrix is idempotent, which is is similar to itself for this reason. And the eigenvalue is so 0 or 1. Now, how to compute these projection matrix? Now, the way to compute these projection matrices is by an analytical tool which is called the singular value composition. You don't do it. You write SVD. You saw how I computed the eigenvectors 2 days ago. A, okay? Now, SVD is SVD function, okay? By MATLAB, you write SVD, that's it. So usually, I gave you this insight about the rotation matrices so that you know how the computer computes the decomposition into triangular matrices, and but it's just a flavor for that. Now, so what is the SVD? Now the SVD says, suppose that I have a matrix. The matrix is complex and it is n times n. Okay. And what I can do is, there exists this decomposition such that I can take this matrix A and B and N, can be decomposed into a square matrix U, a diagonal matrix sigma, and another square matrix B. Now, the matrix U and V are unitary matrices and are orthonormal. Okay? So, that means that, by the definition of orthonormality that we gave today. Matrix sigma is, so now just to visualize the picture, okay? So you have a matrix that is, let me say, tall. This can be decomposed into a matrix U a matrix that is and then a small one. Okay, so I have this. Now this is V permission, and then you have a matrix sigma. This matrix sigma contains only the entry along the diagonal. Okay, so these entry are sigma, so it's called sigma 1, sigma 2, and is indicated in compact form in this one there. Now they keep on filling along the diagonal until the minimum between the row and the column of the matrix A, which is indicated by that. Okay, so practically, visually is the following. So I keep on putting along the diagonal until I reach this point. So, okay, so that means that for sure this part is 0 because there is no entry along that part because the diagonal is finished. Okay. So if this one is n time n, okay, this is n time n, set. So this is this part which is left out is m minus n. Okay, and the first part is the minimum between n and n. Then, what are the properties? The properties are the following. If these singular values are ordered in decreasing values, so which means if the sigma 1 is larger or equal, sigma 2 is larger or equal, blah 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 is larger or equal sigma r, then equal sigma r plus 1 equal sigma minimum. These are equal 0. So which means if the first r singular values are different from 0, that means that the matrix A has a rank R. So the number of singular values different from 0 define the rank of the matrix A, which means define what are the dimensions of the Bug subspace. Now, again, once more, we know that the matrix U can be decomposed in two parts.
Right here is better. It's larger.
So, the matrix U, which is the one that is big, okay, can be decomposed in two parts. U1, U2. U1 is composed by R columns. U2 is M minus R. So the remaining part. Okay? Then I write it in a big way. Okay? So that one is, I said all the entry. And then for some reason, this is R. Then they continue along the entry. But these are all 0. These are the singular values, so it is sigma 1, sigma 2, blah blah, sigma R. Then similarly, I have the square matrix V, okay, V emission, and the square matrix V is itself is decomposed in two parts. Which includes, we have rows, and is n minus 1. Okay, this is the size of the problem. So remember, I started from it. So, you know, by looking at the singular value, the sigma, simply looking, okay, so if I make a plot of that, imagine, you know, I make, if you open MATLAB, you put a matrix, then the matrix, you know, should not be symmetric, so it's any arbitrary matrix. You put these matrices into A, then you calculate the singular values, and then you plot the singular values. Make a plot of the set of sigma. Okay? When you plot the singular values, since that these are ordered, what you see is that they're this way, and then they're zero. Okay? So since, I don't know, imagine that you do with MATLAB, with the matrix, how big was the matrix we were working 2 days ago? 100? 1? Okay. Imagine that M is equal to 100, okay? Then, I don't know, this R can be 30. Just a second, okay? This is R. Why is R? Because, you know, if I take 31, the singular value is 0. 32, the singular value is 0. Okay? So this is the plot of sigma. So what I can say that the size of the matrix A is 30. What does it mean? It means that this subspace is 30. So the subspace of the columns is 30. So 30 is the dimension of the subspace that I need. 200 minus 30 is the noise. So in 200 minus 30 there is a noise. By the way, we close the bracket, open the bracket, by the way. I remember when we were doing the MATLAB 2 days ago. At a certain point, I computed the eigenvalue of the projection matrix, right? And they were 1, boom, 0, right? Okay. I mean, if you count how many were ones, if you know, the plot was something like that. And then all the others 0. Was it that? Okay, so this is 1, 2, 3, blah, blah. That is the number. So if you see the number, this is the rank of the problem. That is the rank of the problem. So the problem that we were working and we saw 2 days ago, the problem about predicting the data itself had only whatever, I don't know, this might be 15 or something. Okay, so 15 were the true degrees of freedom of the problem. So you made, think about that, we made 200 measurements, okay? We predicted with 200, but the real degrees of freedom of the problem is not 200, it's 15, I don't know. I mean, if you have the MATLAB open, you can see, okay? It's very smaller. So it's like, it's in this case, I don't know, in this, I mean, this example that I made, this 30. The real dimension of the model is 30. It's not 200. So that means that I'm wasting some of the dimension. That means that probably I can, I can implement in a more efficient way. Now, this is one remark, but let me continue that. So since U1, U1 here is describing the subspace of A. Oh, nice. So that means these columns, so this one, blah, blah, up to the R, okay, so it's 30. So the first 30 columns out of 200, because M, you say, is equal to 100. The first 30 columns are describing that subspace, which is the subspace of the model. This one is describing the noise. Now, but these columns are much better than the one that I described. these columns are better than the column of A. Much better. Why? What are these? They are orthonormal, right? So what does it mean? It means that even if A1, A2 are, tilted in some way, these U1 and U2 are orthonormal one another. So I found a reference system U1, U2 that is orthonormal. Beautiful. I always try to have a basis that is orthonormal. Think about it. Try to use the sinusoid, right? It's orthonormal, the sinusoid, no? So every time you can, you try to put your orthonormal basis. So orthonormal basis, okay, as much as you can. So we found a way to describe that subspace. And by the way, I said I want to have a projector. Excellent. How do I get a projector? Now, if I want to make a projector, I do this way. Since U is a set of vectors, and this set of vectors is describing the subspace of the data. So let's see a very easy way how I write the projector all together. And so my projector is the following. So what I need to do, I need to take any vector, say B, I multiply by U1 transpose. Now if I take a vector B and I multiply by U1 transpose, what do I do? I take every vector basis and multiply B by the vector basis. Let me sketch where. I put a new page. It's better. Because this is. So let's make U1 transpose B. Okay? Now this is not yet a projector. This is the basis. So I said, if I have a A1 and A2, these are the two columns. Now the basis is U1, U2. Okay? They are orthogonal. Okay? Now, so what I do with this U1 transpose? This U1 transpose is vector U1, now is a vector. Vector U2, vector UR, multiplied by B. Okay? So, which is a vector, is U1 transpose B. So, which means, I take a vector B and I calculate the length of the projection of vector B. On where? Onto the direction you want. So if I have B, this length is U1 transpose B. And this one is U1. What do you call? You call versorial. What do you call it? Unit length vector. How do you call in? Give me a word because I adapt easily with you. Versor, versor, unit vector, unit direction. Okay, I call it I call it unit basis. So this is U1 transpose B. Okay, that's a length. And then if my second vector is U2 is pointing in that direction, then this one, this length is U2 transpose B. A length. U1 transpose B is a length. It's not a vector, it's a length. Okay? So U2 transpose B, blah blah, until I have UR transpose B. Now, what you want to do, you need to say, okay, so this U1 transpose B now should be multiplied by U1. Okay, so let's make it. So I take this length, then I say, so I have a U1 transpose B, which is a scalar. I multiply by U1. Okay, now this one is a vector. Okay, this is u1 transpose v multiplied by u1 is a vector that points in that direction. That one is u2 transpose v is a length. So I say this vector in this direction, this versor, no, in that versor I have a length that is 3, and then I need to say 3 multiplied by u2. Okay? So if I call it, I don't know, you might be, if I call it this one as the u1x, this one as 1y, I don't know, you probably indicate this way. 1x vector, 1y vector. You indicate it the other way? You prefer this way? That's the best, okay? So if I need to say, how is B? B vector is the component x, u1x, plus the component y, 1y. You recognize that? Okay, what is this? This is the length on x, and that is the length of y. Okay, that's what I'm doing. Now, if you assemble all that, so if you put everything into the same formulation, then you get that what you need is u1 transpose multiplied by v, and this is giving you b projected into a. So that means that this one is the projection matrix. So the projection matrix obtained by the first arc columns. How do I know arc? Because I look at the singular values. I'll count the singular values, how many are different from 0, and then you know from the number that are different from 0, I get the dimension of the column that I need to get. So since the others are equal to 0, then you know I can manipulate further. So this property is important, we say. Okay. So this property is very crucial. That the projection matrix is u1 transpose, or u1 emission in case it's complex. Okay. So that is, now we know how to get the basis for this subspace. And we will use it. By the way, a very common mistake, okay, now, a very common mistake. We know that, you know, if I take all the columns, this property holds, which means, you know, the matrix U is orthonormal itself. Because the matrix U contains, this is the matrix U, contains n columns. And these n columns describe the space. So I can make, you know, the orthonormal, I can use the orthonormal property. But if I consider U1, now U1 is a subset of vectors. Now U1 is orthogonal, the vectors are orthogonal with itself. So U1 emission U1 is equal to identity. The identity is a dimension R. But this one is different from U1 emission because this one is a projector. The common mistake is that you get confident that you can move the emission back and forward. You can move the emission back and forward there because it's the full dimension of the space. You cannot move the emission back and forward here because one is the projector, the other is the identity matrix. And I'm done for today.